Well, good morning. Welcome. Entering the parallel universe of the Vector API. Before I start, let's just have a quick show of hands. Who's heard of Azul? Okay, most people. Okay, good. Well, I'll probably mention a little bit more about what we do right at the very end. I'm Simon Ritter. I'm the Deputy CTO at Azul. And, well, I've been involved in Java really right from the very beginning. I actually joined Sun Microsystems way back in February of 1996, which actually makes me feel really old because it wasn't even my first job. So, first thing is, let's talk about the Vector API. And so obviously somebody requested this particular feature here. And so I thought, right, let's talk about the Vector API. And the Vector API is java.util.vector. And what we have there is the ability to have a collection of, in this case, strings, and we can create a new vector of that type, and then we can add strings to that, and we can determine the size of it and all sorts of other things. That's not what we're here to talk about today. So don't be alarmed, we're not talking about something that was introduced in JDK 1.0. This is much newer technology. What we are going to talk about is the ability to use vectors in the Java language through a well-defined API. But before we get to that, there's some background information that we need to talk about. And the first of those things is understanding the difference between concurrent execution and parallel execution. This is one of those things that often people get a little bit confused about the difference between what is something that's happening concurrently versus what is happening in parallel. So let's drill down into that and make sure that we really have a clear understanding of that. Concurrency. Concurrency is where we have two or more tasks that start, run, and complete in some overlapping time period. So the most important thing about that is if we say we've got two different tasks, we start task number one, and we start the second task before the first task finishes. So there's an overlap in terms of the time of when those tasks are actually running. However, as a very key thing here, there is absolutely no guarantee when we're dealing with concurrency that those tasks will actually be running at the same time. Even though they overlap in terms of the time when they're executing, there's no guarantee that they will be executing at the same time. So that's concurrency. Parallelism is where we have two or more tasks that do run at the same time. So it's very much the case of we have them executing in parallel at the same time. So you can have concurrent and parallel, or you can have concurrent and not parallel. And again, if we look at that in a little bit more detail, we can say high-level concurrency. We could say we've got more than one machine, two people using a word processor, one person starts editing a document, another person starts editing a document, and you're editing the document at the same time. In this case, you may well have parallelism because you've got two separate machines and people could be editing that document at the same time. We can then have machine-level concurrency, where we have a single CPU and we want to have multiple tasks that are executing on that CPU. This is where things start to get more complicated because we need to involve the idea of the operating system and have something like a time-sharing operating system that enables us to give the illusion of parallelism, even though parallelism isn't actually happening there. We've only got one execution unit. So what that means is that we can only do one thing at a time. As I'm sure you know, with the time-sharing operating system, what we do is we run one particular process for a certain period of time or until it blocks on I/O, and then we switch to another process and run that for a certain period of time. And then we switch to another process and so on. If we do that quickly enough, we can give the illusion of parallelism because we can make the person who's using it think that they're actually doing more than one thing at the same time, even though we've got only one execution engine there. Now, clearly we can take that to the next level and we can say, right, let's put more than one CPU in the machine, and then we can have both concurrency and parallelism. We can do things concurrently by time sharing our processes, and because we've got more than one CPU, we can actually execute one sequence of instructions more than one sequence of instructions at the same time. So we have both concurrency and parallelism at the machine level. And then if we drill down to the third level, looking at the processor itself, then we could say if we've got a single core processor, then we can only execute one thing on there. So we can do concurrency by time sharing. We could have dual core or quad core, and that will enable us to have both concurrency and parallelism. One of the big advantages of doing that at the processor level is that we can also have benefits from things like the cache being shared between different processors running on the same processor using different cores, and that will give us better overall performance. So we can have a number of different things that we can get in terms of improvements in performance by looking at how to drive both concurrency and parallelism at different levels in what we're doing. Okay, so let's talk a little bit about concurrent programming in Java. And one of the things about Java as a language is that the approach that the designers of the language took was a little bit different to languages at that time. So if you look at C and C++, they didn't have concurrency built into them exactly. You really had to rely on a different library to provide support for that. So in the case of Java, right from the very beginning, we had this idea of being able to execute multiple threads of execution. So we had the thread class built in from JDK 1.0. This was very good because it did say that, if we created a runnable or we implemented a runnable interface with a particular class, we could have a method, we could pass that to a thread, and that method would execute in a separate thread. Depending on how many cores or how many processors we had, we could either do it concurrently or we could do it in parallel. Now, that was good because it meant that it was very easy to create multiple threads of execution. The hard bit came when you wanted to actually have multiple threads of execution that would work cooperatively. So if you wanted to share data between those threads, things started to get a lot harder because you needed to make sure that if you've got multiple threads trying to access that data at the same time, you don't overwrite changes and you get loss of data and things like that. So if you look at the thread class, you've really got 4 basic primitives that you can use to do concurrent programming where you're cooperating between different threads. You've got wait, sleep, notify, and interrupt. And using those is very difficult to write reliable multi-threaded code. We've also got things like synchronized blocks, we've got the semaphore associated with a class, and so on. To get around that, we had the introduction of the concurrency utilities. JDK 5, JSR 166, the concurrency utilities, introduced a set of higher level features that made it a lot simpler to write cooperating multi-threaded code. Things like semaphores, mutexes, read-write locks, fairly standard techniques that have been available ever since multi-threaded programming had been invented. So that did make life a lot easier. But still, trying to write heavily multi-threaded, heavily concurrent, and heavily cooperating threads was still quite difficult. So we took another approach in JDK 7. JDK 7 introduced the fork join framework, and what they said was, let's take a task which we can break up into multiple subtasks. And we'll do that in such a way that we take our initial set of tasks, our set of data, and we'll separate that into, let's say, 2 different subsections. And then we'll do that recursively so that we can break up those 2 sections into a further 2, and then those 2 into a further 2. And we'll keep doing that until we get to a small enough set of data, a small enough piece of execution that we can then assign that to a thread. The great thing about the fork join framework, I'm sure most people here have used it, is that the framework takes care of a lot of the difficulties for you. So all you do is you say, right, here's my set of tasks, here's the way that I want to break them up, here's the work that I actually want to do when I've got a small enough unit of execution, and let the framework take care of that for us. So it was a great way of approaching that type of execution that you wanted for multi-threading. JDK 8 introduced another approach to how we could do things in parallel and things in concurrently. Lambdas and streams. Suddenly, Java has a more functional style of programming. Again, the idea was that the library would hide a lot of the complexity from the developer, so you don't have to think about it. What was actually being used underneath was the fork join framework. And what we could do is have something like this. So we've got a list of words which we get from somewhere, and then we can create a stream of those words, pass it into an intermediate operation, in this case map. We'll map it to uppercase words, and then we'll collect it into a new list as a collection. Now that is a sequential stream, so it happens sequentially. If we wanted to make that, now this is the tricky bit, do we make it parallel or do we make it concurrent? Actually, really what we're doing is making it concurrent, but we'll say it's parallel. It's a little bit sort of like disingenuous almost in a way. So we'll call it a parallel stream, even though really it's a concurrent stream. And what happens here is that we can say, right, let's take our list of words, generate a stream of that, and then have the fork join framework underneath through the streams API, split that up into a number of separate streams, have them execute concurrently, maybe in parallel, and then bring the results together at the end. Again, we as a developer don't have to worry about even using the fork join framework or anything like that. We simply say, make it into a parallel stream, and that's what we want. Now that's good, but of course it has some limitations, because if we're doing something like this, we can end up with non-deterministic results. And what I mean by that is that because we're splitting up the stream of words from our list, the way that happens might be different depending on when we run it and how many times we run it and what machine we run it and so on. So the list that we get at the end might be in a different order depending on which time we run it and so on, versus the sequential stream will always give us the same order because it's the order from the list that's being passed through that stream. With a parallel stream, we don't necessarily get the same order. Now, the other thing about this is to be a bit careful, because don't assume that doing things concurrently will always do things faster or even more efficiently. If you look at the way that streams work especially, you can say that some operations that we have will decompose well into concurrent operations. So if you look at things like sum and min and max, thinking about it logically, when you want to find the minimum value of a set of data, you can break your data up into different sections, and then you can find the minimum of each of those sections. And then in the next level, you can say, right, use that as your set of data, find the minimum of all those values. So it's easy to break them up into a number of sections for your data, have them execute concurrently, and get better performance, because you're not having reliance between one part of the data and another part of the data. However, some operations don't decompose well into multiple threads of execution. Sort is a good example. So we want to sort all of our elements into the order, from low to high. When we break it up into sections, yes, we could sort each of those sections, but we're not going to have a guarantee that when we put those sections together, that the order will be correct in terms of the sort order. There are algorithms which are designed for that sort of approach, like merge sort, but it's still one of those situations where if you look at the efficiency of it, sorting is not going to be as good as finding the minimum or finding the maximum. The other thing to bear in mind when you're using parallel streams is don't use them where you're dealing with things like I/O. If you've got a file that you're reading, the reading of that file is going to be inherently sequential, so you don't necessarily want to use a parallel stream on that, because trying to break that up into multiple streams is very difficult. Yes, again, there are techniques that can be used where you say, okay, let's have different points into the file and read those concurrently, but it makes the code a lot more complex, a lot more harder to use. So concurrent programming can use multiple execution units to possibly improve performance. It doesn't require them, and it doesn't guarantee to improve performance. Okay, so now let's move on to the idea of how we can apply some of this sort of theory to using vectors, and in this case, single instruction, multiple data, which is what we're actually going to be using here. So first of all, let's talk a little bit about vectors and mathematics. So here I've got two vectors. Now, a vector in mathematics is something that is represented by a set of values rather than a single value. Single value is a scalar, a set of values is a vector. So here I've got two vectors, which are 3 by 1 vectors, 4, 3, 7, 3, 5, 2. If I add those two vectors together, I get the results 7, 8, 9 as a third vector. However, if you do vector mathematics and you say, I want to multiply one vector by another, things are a little bit different. So you can only multiply a 3 by 1 vector by a 1 by 3 vector, and the result is actually a scalar. You have to multiply 2 by 2, 3 by 3, 4 by 4, add up the results, and you get a scalar 29. The reason I'm telling you this is because vector mathematics is different to the vector API that we're going to explore on the next few slides. Single instruction, multiple data. What this allows is true parallel processing within a single execution unit. And the idea behind it is that we use a very wide register. Very wide register enables us to hold multiple values at the same time, and then we can take information from, let's say, an array, populate our vector with that, and then we can have a certain number of what are called lanes. So the number of lanes is the number of elements that we can store in that very wide register. Now, if we want to process some data, typically how we're going to do it is using iteration. So we'll typically use a loop to process something. I've got an array of 4 elements, and what I want to do is add the value of 2 to each of those. Now, if I do that with simple iteration, what I'm going to do is I'm going to go through the list and go 10 plus 2 is 12, 14 plus 2, 16, 11 plus 2, 13, 8 plus 2, 10. If we want to use single instruction multiple data and a vector to do that, what we actually do is we say, let's take a very wide register. In this case, we'll have one that's big enough to hold 4 values. So we put those 4 values into our very wide register. And now we can apply that operation of adding 2 to each of the values as a single operation. So it's a single clock cycle which adds 2 to each of those values and then updates the value in the register. The important thing to get across here is that unlike a normal register that we would use where it represents, a 64-bit value or a 32-bit value, and we manipulate that by doing addition or whatever, here the instructions that are used by the processor are sophisticated enough to understand that in this case we have 4 lanes, so we have 4 distinct values in there, still represented by bit patterns within the register itself. But rather than just adding 2 to the register, it adds 2 to each of the lanes within that register. So it has to know what the size of the lanes are, how many lanes we have, and so on. And then the operation can be applied as a single clock cycle by adding 2 to each of those 4 values and generating 4 new values. Obviously, it also has to be clever enough to understand about overflow, because you don't want one of those values overflowing into the other value. So the instructions are aware of the fact that each of those is treated as if it's independently, so there isn't overflow into the next element in the register. Single instruction multiple data has been around for a long time. It's actually been around almost as long as I have. 1966. I'll bet nobody here can actually recognize this machine. Anybody got any ideas? No, I didn't think so. I thought this one probably would defeat everybody. This is an ILIAC 4. Okay, so next question. Has anybody ever heard of an ILIAC 4 before? Oh, one person over there. Right, a couple of people. Okay. And there are a couple of other machines that also from the 1970s. We had supercomputers. We had the CDC Star 100, the Texas Instruments ASC. These are, the kind of computers I really love because they fill an entire room. That's a real computer. Of course, if you look at that, you probably find that there's less processing power there than there is on your iPhone. And of course, the one that everybody remembers when it comes to vector operations is the Cray 1. Again, a fantastic computer because it has a sofa built around it. So that is a real computer. Right, so that's where single instruction multiple data came from the very beginning of really big supercomputers. Now, what we then found was that the processor designers started to add these kind of features to the processor level. And so I've just kind of given a brief history here of single instruction multiple data. I won't go through all of it, but basically, back in the mid-90s, this was when it became popular because people started doing a lot more kind of multimedia type of stuff. Desktop computers were playing video, they were doing graphics rendering and things like that. So it actually made a lot of sense to have this ability to do numerically intensive operations quite quickly. So back in 1994, HP started off with PA RISC. 95, we had Sun Microsystems, who I used to work for, UltraSpark processor. And then 1996, Intel got into this, and they added the MMX instructions to the Pentium 5, P5, and that was only 64-bit wide registers. But of course, back in those days, remember, we had only 32-bit instructions and data, so it was really sort of two lanes that you could have for 32-bit values. Pentium 3 gave us 128-bit registers and the streaming SIMD extensions, SSE. And then 2011, we got the AVX instructions where we started moving up to, again, 128-bit registers, AVX2, 256-bit, and the current biggest one in the Intel architecture is the AVX 512, which funnily enough has 512-bit registers. Okay, so the Vector API. Interestingly here, the Vector API is an incubator, meaning that it's been included in the JDK, but it's not a final part of the JDK yet. So it's an incubator module that's available from JDK 15. It holds the record as being the longest incubating API that we have in Java so far. So it's the 7th incubator, as I say, in JDK 22, JDK 23, it will be an 8th incubator. And it will continue to be an incubator until Valhalla becomes part of Java. So the designers of this have said that because it's related heavily to Valhalla and some of the introduction of things that they're doing, they're going to have to wait until that becomes part of the JDK before they can finalize it. Realistically, I wouldn't expect to see many changes between certainly JDK 21 and when we get to the final version. Okay. So let's look at what we actually do with vectors in Java. So the first thing is to have our register. So we've got our register, and let's assume we're using AVX2, so we've got 256-bit wide register. We'll represent that with a very imaginatively named vector class, not to be confused with the java.util.vector class. This is going to be one that has a generic type parameter, so type parameter of E, which we can use to represent what we're going to store in that vector. And if we then say, okay, we'll create a vector of type integer, meaning that we want to store int values into that vector, what we're going to end up with is effectively this. So we'll have the very wide register, 256 bits. Because we're storing 32-bit ints in there, we can divide it up into 8 lanes and have 8 ints stored simultaneously. One thing to kind of get across here from a performance perspective is that because we don't have Valhalla yet, we can't have a vector of ints. So we have to have a vector of a real Java type, not a primitive. So in this case, we'll have a vector of the wrapper class integer. But the important thing from a performance perspective is that there is no boxing and unboxing happening here. So even though we talk about it being a vector of integer objects, what actually gets stored in the vector is just ints, so primitives. So we don't have to go through that boxing and unboxing as we put objects in or put values in and take values out. So that gives us a number of lanes, in this case 8 lanes, which are the places where we can store the values. In terms of the vector class, what you get are a set of methods which represent operations which are common to all vector types. And in this case, they're the ones you'd expect. So we can do addition, we can do subtraction, division, multiplication, we can do minimum value, maximum value, and then there are some others beyond that. So all the things you would expect which are common across all vector types. What we then have is a set of subclasses of that, because the vector class on its own is an abstract class. You can't instantiate it directly. So what we then do is we create a set of vector subclasses which represent the primitive types that we have in Java. Byte vector, short vector, int vector, long vector, float vector, and double vector. There is no Boolean vector, and there's obviously no char vector as well. So all of the primitive numerical types are dealt with there. They add some more methods to the ones that you get in the base vector class, specifically things like from array. Now, when you're doing from array, obviously you would need to pass in an array of the right type. So that's why they're type specific and specific to that particular subclass. So we go back to our classes that we would have here. So now, rather than just talking about a vector of type integer, what we're going to have is an int vector, because that's the concrete class that we can instantiate to represent the vector that we want to put our values into. Then we get another class which is called vector shape. This is a really bad name, because a shape, if you think about it, is a geometric representation of something. It has vertices, it has edges. What we're talking about here is actually a size. Now, I have no idea why they didn't just call it vector size. I mean, there's no reason not to call it vector size, because that's what it really is. But they decided to call it vector shape. And as you can see here, because we have a 256-bit wide register, what we end up with is a value which is s_256_bit. Clearly in Java, you can't start a variable name with a number, so we have to put s_ in the front of it, just to simplify things. In terms of the values that you can get for a vector shape, or really size, we have 64, 128, 256, and 512-bit. And then we also have one which is max bits. So that would represent the maximum size that we have available to us. And again, design decision, you wonder, why did they not capitalize max? Because if you're going to capitalize bit, why did you not capitalize max? But there again, I mean, you know, these are small things, but they irritate me. Yeah, that's true. Oh, yes, good point. Yes, it's an incubator module. I will log, I will make my displeasure known to the developers and see what difference it makes. Right. Okay, so vector shape, back to that. So yeah, so the max bit represents the biggest register that we have available on the current machine. This is good because it enables us to write cross-platform code where we don't need to tie our code to a specific microarchitecture. We don't need to say to ourselves, right, I know I've got AVX2 on that machine, so I'll write it with 256, or I've got AVX 512 on that machine, so I'll use 512. What I can do is just simply say, give me the biggest register that's available on that machine, and then we'll work with that. And we'll see in the examples that we've got coming up how that actually works. The other thing to be aware of is on the Intel architecture, it does support more than one size shape. So you can have a 128 or a 256-bit value register if you want to. On ARM processors, they only support one size or shape, and you have to use S max bit for that, because it can be anywhere from 128 to 2048. That's a really big register. That is very much vendor specific, so it depends on whichever implementation of the ARM architecture that you're using, whether it's Apple Silicon or whether it's a Snapdragon processor. It will be dependent on what they actually implement in that. So you just use S max bit on an ARM processor and it'll give you whatever's available there. What that then leads to is another class, which is a vector species. And a vector species is really sort of like the summary of what we're dealing with in terms of our vector. Vector species as a class is again generic, so it has a type parameter associated with it. And what you get is a combination of the element type and the shape. And so if you print out a species, you'll get three values. Three values are the type that's being stored in it, so int or float or whatever, primitive type in the lane, the number of lanes, which in this example is 8, and the size of the register, 256 bits. So it gives you all the information about what we're using in terms of that particular vector. So the vector species, where we've got a particular register, and then we're storing ints in it. How do we go about using this? So what we can do is use the fact that we want to use the maximum number of bits or a particular size, but we can then use that to calculate how best to populate our vectors. So what I've done here is I've created a vector species of integer, and I'm using int vector.species256. So it's an integer vector which fits into a 256-bit wide register. And then what I can do is have some big arrays which have got 1 million elements in them. What I then want to be able to do is to loop through the data that I've got and divide up that data so that I can populate the vector for each iteration of the loop. So I need to fill the 8 values that I have available for each iteration of the loop. And I can do that by finding the loop size and the number of lanes. So number of lanes is easy because that's just going to be how many lanes I have in the vector, 8. But the loop size is where I can ask the species that I have to tell me how many times I have to go through the loop given the number of lanes that I've got. So I say, give me the loop bound given the length of the array that I've got. So it'll say, take 1 million, divide it by 8, and give me a number of how many times I need to iterate through my loop. Clearly, if it doesn't quite fit into that, if it's not a round number, it'll give me one more so that I guarantee that I've got enough iterations to process everything in my array. What I then do is obviously create a loop where I loop through and I say, do the loop size number of iterations and increment by the number of lanes each time, so I'm moving to the next set of data that I need to populate into my array. And then I simply say, call int vector with from array to populate the elements of the lanes using my array and from the index into the array that I'm currently at. And then I just use the vector. What I can also do is I can use a vector mask. And this becomes more significant when we need to deal with arrays which won't fit into a complete number of iterations for the loop. So if I've got a number of lanes which is 8, and I've got, let's say, very small, we've got 12 elements in my array, clearly I can do 8 for the first one, but I only need 4 for the second iteration of my loop. Using a mask, what I can say is ignore the elements in, or the lanes in that vector which don't have values in them. So if I've got 4 lanes in use, I can mask out the other 4 lanes so that it doesn't have any impact on the operation that's taking place. So in the example I've got there, 30 elements, 256-bit, 8 is the number of lanes. So I do 3 times 8, and then I've got 6 left over. And so I mask out the final 2 elements. And quoting from the spec here, it says, an operation suppressed by a mask will never cause an exceptional side effect of any sort, even if the underlying scalar operator can potentially do so. So it basically just ignores those elements in the vector. Again, if we show an example of how we would use that, same thing that we've got here where we've got our loop through there, all we would do is we'd say, okay, create a vector mask which uses the index in range and simply says, right, so when I get to the end of my array, where I've got the last few elements, create a mask that will then mask out the ones that aren't actually relevant in there. Apply that mask to the from array method call, and my vector will be populated in the correct way. We can also use it to perform conditional execution for a vector. So we can say, okay, let's create a mask for our vector, and then we can filter out things that we don't actually want to reference. So we've got 2 different vectors there, and then we can combine them using a particular mask. So that on its own, sort of, you think to yourself, okay, well, what does that actually mean? And what we can do here is, if I show you a better example here, let's say we've got 2 vectors which have 4 elements in them, and the mask that I'm going to use is 0, 1, 1, 0. What I'm going to create as the result of that is if the mask is 0, I take the element from the first vector, and if the mask is 1, I take the element from the second vector. So I'll get the first and last element from the first vector, and the two middle ones will come from the second vector. So it allows me to select different parts of the vector or the pair of vectors to then generate a third vector which has those values in it. We could also do a vector shuffle, and this allows us to reorder the elements in our vector. So get our vector A, then we'll have a set of shuffle values, which is essentially saying, take the elements at this position and then put it into the lane in the position it is in that array. Call vector shuffle from values, use the shuffle values, and so on. Again, simplified if we see an example here. So if I say that I've got 0 through 7 are the values I've got in my vector, and I want to apply that shuffle values to that, what I'm going to do is take 0, then it's going to be 2, then it's going to be 4, then it's going to be 6. So 1, 3, 5, 7. I'm effectively interleaving the values that I have in the first vector into the second vector. There are definite situations where that's useful when you're doing these kinds of operations. So it's available as a simple API. You can simply specify the shuffle values and reorder your vector. What can we do once we've got our vector? Well, lots of different things. So there are a whole set of operations that are available through the vector operations class. Look at the documentation for a full list. You can break them down into these different types. So you've got associative ones where you're basically saying the order doesn't matter. So you're doing an add or an and. Doesn't matter whether you add A to B or B to A, it's going to give you the same result. Same with and. Binary ones have 2 arguments, but the order does matter, because if you divide A by B, it's different to dividing B by A. Same if you take the power of something, A to the power of B could be different to the B to the power of A. We have comparison operators, so we can do equality, not equal, less than. We can also do greater than. Conversion, so you can do double to byte, byte to float, float to double, and so on. There are some ternary operators. Well, there's actually one, I think, which is one that takes 3 arguments, and in this case is what's called FMA, fused, multiply, and add. It seems that when you do these kind of vector operations, multiply and add is a very common sequence of things to do. So they have this FMA where you can specify the thing to multiply by and then the thing to add, and it does it all in one go. We also have some tests, is finite, is negative, and then some unary operators which only need a single value, which is taking the log of something, negating something, or the Boolean not of something. If we want to use those, we can chain them together and do something like this. So here what I'm doing is I'm saying, okay, I've got an array of values. I want to calculate using Pythagoras. So I want a squared plus b squared square root of, square root of. So now I can say, okay, here's my float vector, populate that with the values from my array, take a second one to create the values of b, and then I'll create my new vector c, which I'll say multiply a by a, add b by b, and then take the square root of that and give me the result. So we'll do all of that in a single set of operations. Reduction operations. These are also possible. So this is quite interesting. What you can do is you can say, right, rather than applying the same operation to all of the lanes individually, you can then say, take all the lanes within my vector and then reduce it to a single value. Here what I'm doing is saying, okay, let's take an average of the values in my vector. And so we create the mask, we do the various things there, we can create the vector from the array using our array species and so on. And then in terms of the operation, we'll say that we'll reduce the lanes to the sum of the values in that vector. Now, this is where having the mask becomes even more important, because obviously if you've got values that aren't being used at the end of your vector, then you don't want them to be involved in that reduction, because they're clearly not values that are part of the array. So you want to ignore them. So the mask is very important when you're doing something like a reduction. So here we're doing reduce lanes, vector operations add. So we're adding all the lanes together and then producing a result, which then we can use to generate the average. How well does it work? So this is another interesting sort of discussion. Right, so single instruction multiple data is fast. Yes, great. So we can do things truly in parallel. We can process multiple elements of our array in a single thing. But, remember, main memory access is relatively slow. So we look at the kind of typical times that it requires to access different memory within our system. L1 cache, which is the fastest, takes about 3 to 5 cycles. L2 8 to 20, L3 about 50 to 80, and RAM realistically is 100, well over 100 plus cycles. So the closer that you have your data to the processor, the more benefit you're going to get from being able to do these things in parallel. The more you have to wait for the values to be brought from memory, then the less implication or less impact you'll see from the ability to do these things in parallel. So the further you go away from the processor, less improvement you'll see with using single instruction multiple data. Now the other thing you've got to remember is that the JIT compiler that's built into the JVM actually understands about vectors. It knows that there are vectors in the architecture, and it knows there are vectors in the instruction set. So it will use them if it can. This is what's called autovectorization. And so what you'll find is that the JIT compiler, where it sees things that can use vectors, will just do it automatically. The way to find out how much of a difference it makes is to turn that feature off. So if you use the -XX minus use superword option on the command line, that will say don't use autovectorization. So then you can do a comparison between what you get with using vectorization and without. Now, I've taken the following results. I have to give full credit to this. There's Thomas Zeltzer, who wrote a very nice article on Medium, and I thought, right, this is very useful information. I shall use this to represent what you can get in terms of results. So here, what we're seeing is a graph which shows improvement in performance. So that the 1 there is your baseline, and then above 1 is where you're getting better performance, and below the 1 line is where you're getting worse performance. So the baseline is where we're just using a set of arrays and we're using no vector operations in terms of defining them within our code. So we're relying on the compiler to do that vectorization for us. So at this point, we're using autovectorization within the JIT compiler. So the blue line is always going to be 1, and then we look to see what's the comparison between the blue line and the red line, which is where we have explicitly put vector code into our application. And the bottom line represents the number of elements in the array. And this is quite interesting when we look at this, because you can obviously see that the 64 element array, the vectors comes out faster than the auto-vectorization. But for most of the others, they're pretty much about the same, except for 32K, where it drops off a bit. And if you dig into that, what you'll actually find is that this is down to some quirks of how the JIT compiler works. On the 64 element array, it turned out that what was happening was that the JIT compiler was using really a slightly older architecture and not really optimizing for the vectors that were available in that particular architecture. So it came up with worse results than if we did it explicitly in our code. The 32K elements, the fact that we got worse results when we did the code explicitly was because the JIT compiler in that case was doing more loop unrolling. It just happened to be that on 32K elements, it did more loop unrolling than we would get typically with our own vector code. So just interesting to see that. Now, if we turn off the auto-vectorization, then you really see the benefit of using vectors over just a simple array. So here we turned it off, and so again, we've got the baseline there, and you can see that we get much better performance when we're using vectorization. Until you get to very large arrays where you're dropping off and you're seeing like at the 2 million, I should say, elements, 60 million, 134 million. And that's, again, where you're seeing the effect of the time it takes to access the data either from RAM or maybe even having to go out to disk, is where you're going to see that the benefits are eliminated. But for sort of small to medium-sized arrays, you get real benefit from using vector operations. 5 minutes left. Okay. You can do statistics as well. So you can do things like this, where you can look at your vectors and say, count how many elements are, how many things are true within that in terms of less than, equal to, and greater than. So you can simply say, right, I need to know, compare these two vectors, compare each of the lanes and tell me how many of the lanes within there are greater than, equal to, or less than, and we can get a count for that. Again, looking at that in terms of autovectorization, we get much better performance with using vectorization rather than not vectorization, just simple arrays. So that works really, really well. Branches can slow you down. So if we make a situation where we've got a conditional and we say, okay, let's use, we want to add the elements from array A to array B, but only if array B is an even value, that introduces a test that we need to take into account. And if we look at the kind of code that's generated by the C2 JIT compiler, don't go into all the detail about this, but essentially it's not using vector. It's not auto-vectorizing this, even though technically it could. It's not auto-vectorizing it. It's just doing some simple loop unrolling. If we take what we do at Azul, because we create a different JVM with different performance characteristics, we have a different JIT compiler called Falcon based on another one called LLVM. And what we do is we do auto-vectorize that. So we can generate vectorized code directly from that code without having to worry about the fact it's got a conditional on it. So here we're seeing it's bigger code, but in this case, we're using the vector operations and we're doing a bit more loop unrolling at the same time. So it's, again, conditional branches. If you're doing that in your code and you're going to use hotspot, that's where vector operations would be very, very beneficial using the vector API, because then you have the ability to say, I really do want to use vectors here. Just to summarize then, basically the vector API allows you to do explicit single instruction multiple data processing. And there's a lot of flexibility in it in terms of how you can do that by using masks, by using shuffle, by using various techniques like that. All of the operators that you've got available to you, it really does give you a very rich set of functionality that you can use to actually do what it is you're trying to achieve in terms of those numerically intensive operations. Most of the time, for simple operations, the JIT compiler is going to recognize it and auto-vectorize it, so you probably don't get much benefit. For more complex things, especially, like I say, where you've got branches involved and conditionals, then it really does come into its own and generate code that is better in terms of performance than the JIT compiler will generate for you. Again, benefits decrease as the size of the array increases because of that time that it takes to get access to the data, and then that starts to overwhelm the benefit you get from doing things truly in parallel. Ideally, we'd like the compiler to do all of this auto-vectorization for us, but unfortunately, we're not quite at that point yet. So with that, oh yeah, just mentioned Azul Java, like I said. Yep, Java is what we do. We have two things that we do. One is Platform Core, which is a replacement for Oracle's JDK. Exactly the same, drop-in replacement. And Azul Platform Prime, which is our high-performance JVM. Different garbage collector, different JIT compiler, as I've said, and a thing called Ready Now to eliminate warm-up. So with that, I have 1 minute left for questions. Make it count. So did anybody have a question? Oh, over there. Shout.
What are use cases? Why do we need vector API if we can do everything in native and use GenAI?
Right, so the question is, why do we need the vector API if we could do everything using native code and JNI? because native code in JNI is a lot more complicated than using the Vector API. Vector API allows you to do it in Java rather than having to step outside of the JVM, step outside of Java, and having to do it as a more complex way of doing things. So the benefit is the simplicity, I would say.
But when these things are used, there is no question about simplicity. There is a question about performance and which log is counted.
I guess you could always argue that there are ways of extracting more performance out of things. And so I think what you're saying is that, if I really want to go for very high levels of performance, I'm going to step outside the JVM and hand code it in like C or C++, or even get down into the assembler level. This is all about making it simpler in terms of the approach. So you can get better performance for a large number of situations without having to have those high levels of skill to actually go outside and do hand coding of that kind of thing. So I think that's probably the best answer I can give you for that.
I don't agree.
Okay, all right, we'll have to disagree. My time is up, so thank you very much.